For the next example problem that we're going to work through on 2D motion, we throw a ball at a speed of 25 meters per second at an angle 37 degrees above the horizontal, and we want to find how far away will the ball be from us when it lands, what will its maximum height be, and what is its velocity when it lands. So the first thing I'm going to do is I'm going to draw a picture. This picture is going to be fairly simple. Here is the ground level. And we are told we throw a ball initially at a velocity 25 meters per second, directed 37 degrees above the horizontal. So I'm going to draw that vector showing the initial velocity of the ball. So initially, the ball is traveling with an initial velocity of something like this. So V initial, in this case, is a vector. It will have a horizontal and a vertical component. Those horizontal and vertical components of V initial are V naught X and V naught Y. We're going to work with that soon. We are told this is 37 degrees above the horizontal. We assume ground is horizontal unless we're told otherwise. So this is 37 degrees. Now, what is the trajectory of the ball actually going to look like? Well, you could imagine that if you could turn off gravity for the moment, when you let go of the ball will be moving in this velocity, and because we turned off gravity, the ball will just continue moving in this direction at 25 meters per second forever. That's not really what happens in the real world. The moment we let go of the ball, gravity begins to act on the ball, pulling the ball downward. So instead of just traveling in this direction forever, the ball is going to fall. The trajectory of the ball will look something like this, and then the ball will land over here. So what I'm going to do first is, just like before, I will set up my coordinate system. I'm allowed to set up a coordinate system anywhere I want that's convenient. So I choose ground level will be the x-axis, the horizontal axis. So here is the x-axis. And the vertical will be the y-axis. I'm going to place the origin at the location from where the ball is thrown. So here is the y-axis. Now, based on how I drew this picture, is there any numbers we could plug in right away without having to do any type of calculation? And the answer to that is yes. Of these 11 terms written over here, there are 5 terms we could just insert a value for right away. If I look at the location where the ball is thrown from, the ball is thrown from the origin. So this is the initial location of the ball. The origin is x equals 0, y equals 0. So I could write x initial is 0 and y initial is 0. I could look at the final location of the ball. And the final location of the ball, for part A, we're asking how far away the ball is when it lands. The final location of the ball for part A is going to be right here. And that is going to be, well, I don't know how far away it is, so I don't know what x final is. But if you're at ground level, again, your height is 0. So I could say the final height of the ball is 0 as well. For part B, when we're asking about the maximum height, we're going to say the final location is at the top of this arc. And then for part C, we're asking what is the velocity of the ball when it hits the ground. The final location will be the location where the ball lands again. But we will deal with that when it comes. For part A, this is the final location. Okay, I have values for 3 of the 11 terms. We claimed there are 2 more terms that we could insert a number for right now without having to do any calculation. And, well, free fall. The ball is in the air. When the ball is in the air, the only thing influencing its motion is gravity. And gravity has a constant value. The acceleration due to gravity is ax equals 0, ay equals negative 9.8. Gravity pulls downward. So I can plug in ax equals 0, ay is negative 9.8. This is going to be a very recurring theme in many of these problems that we encounter. Okay, so we inserted 5 of the 11 values that describe the trajectory of the ball. Is there anything else now we could insert reasonably easy? I claim the answer to this is yes. So here's what I'm going to do. I said before that the initial velocity is a vector. The initial velocity has a magnitude of 25 meters per second. Speed is the magnitude of the velocity vector. So the initial velocity, this vector I drew in red right here, has a magnitude of 25 and is directed 37 degrees above the horizontal. If I give you a magnitude and an angle, you have enough information to find the components of that vector. So I am going to now draw that vector over here where I have a little bit more space. And I could say, here is my horizontal and my vertical axis. Here is this initial velocity, which is v0. And we know this vector has a magnitude of 25 and an angle of 37 degrees. From what we learned on breaking a vector into its components, v initial will have a horizontal component and a vertical component. I call the horizontal component v initial x, and I call the vertical component v initial y. This v0 x and v0 y, the components of my initial velocity vector, are the same thing as this v0 x and v0 y. So I could use what I know from breaking a vector into 2 components, where I could say v0 x is equal to 25 cosine of 37. And if I plug that number into a calculator, I will get 25 cosine 37 is equal to 20 meters per second. And for v0 y, I will have v initial y is equal to 25 sine 37. And I will hit enter on my calculator and I get 15 meters per second. So I could say v initial x is 20 and v initial y is 15 meters per second, respectively, if you want to include the units. Okay, so at this point the board is cluttered. I am going to ask, do I have enough information to find the distance that the ball travels? So I will erase a lot of stuff here, but you will have this in your notes where you can refer back to the picture. And if I'm trying to find the distance the ball travels, that means I'm trying to find x final. You begin at x equals 0, you end at x final equals whatever. So I want an equation that has x in it. I look over here and I see 2 equations that have x in it. Which equation do I want to use? Well, let's look at them individually. I have this first equation up here, x equals x initial plus v initial xt plus 1/2 axt squared, or I have vx squared equals v initial x squared plus 2ax x final minus x initial. Okay, so let's ask, what do we know? Well, do I know x final? This is ultimately what I'm trying to find. So this is what I really want. It's also over here. Do I know x initial? Why, yes, I do. Do I know v initial x? Yes, I do. I do not know time. I know acceleration due to in the x direction is 0, so that'll get rid of this entire term. So this equation has two unknowns. I don't know x final and I don't know time. Let's see what happens in the next equation. Do I know Vx final? Yes, I do, but I'll explain that in a moment. Here I have an Ax, and Ax here is equal to 0. So that means this entire term is going to just be 0, and that means Vx initial is equal to Vx final. Well, one thing I could do is, if Vx initial is equal to Vx final, I'll just write that here right now, so I don't need to do it later. But this equation will not help me find the final position of the ball. So we got something out of it, but not what we're looking for right now. So what I'm going to do is, I would like to know x, but before I find what the distance the ball travels, I first need to find t. So I'm going to use a different equation to find time. I'll get a number right here. I'll take that number, I'll plug it in there, and then I'm good to go. So we are on a side quest. Our goal right now is to find time, and then we'll be back to our main quest to insert that and find position. So what can I use to find time? Well, it's not going to be true 100% of the time, but very often if you want to find time, you will want to use an equation on the y side. So let's look at these y equations. Time is here and time is here. So let's look at the first one. Y final is equal to y initial, v initial yt, 1/2 ayt squared. So we have this equation for the height of the ball, and we are going to look at it. We're going to ask, for every term in it, can I immediately plug in a number from this list over here, aside from time? And if we can do that, then we could solve for time, plug into the previous equation, and we're golden. So the final height of the ball, do we know the value of that? It hits the ground, so the final height of the ball is 0. Yes, we do know that. The initial height of the ball, we are assuming we throw it from ground level. We have a number to plug in there. Now, technically speaking, if I were to throw a ball, I would do something like this, and the ball, when I let go, would be about 2.5 meters above the ground. That is not 0, but we're just going to wave our hands and say, assume the ball is thrown from ground level for the purpose of this problem. If you're not told explicitly the height at which the ball is thrown from, assume it's thrown from ground level, a height of 0. Do I know the initial velocity of the ball in the vertical direction? Yes, I do. Time, that's really what we want to find. I know the acceleration due to gravity in the vertical. Again, time, that's what we want to find. So this is great. I could plug in numbers, solve for t, then I could come back to this equation and solve for x. So y final is 0, y initial is 0, plus v initial y is 15 times t. T is what we're ultimately trying to find here, plus 1/2. Acceleration in the y, negative 9.8 times t squared. So I could simplify this equation as 0 is equal to 15t minus 4.9t squared. 1/2 times 9.8 is 4.9. That's just a number that comes up very often, so at this point it's committed to memory. What I'm going to do next is I'm going to leave the physics behind for a moment and do some math. So I could write this line as 0 is equal to t times 15 minus 4.9 t. I could write this line like this. Now, if you don't quite believe me, you don't see how did you get from here to here, just begin at this line, factor in the t into the parentheses in both places, and when you do that, t times 15 gives 15t, t times negative 4.9, t gives negative 4.9t squared. So before we think about what we're doing here in physics, let's think about what this equation is really telling us. When I have an equal sign, whatever I have on the left side of the equal sign must be the same as whatever I have on the right side of the equal sign. So 0 must be equal to all of this stuff. Now all of this stuff, I have a term multiplied by another term. So either I have two possibilities. One possibility is this term is equal to 0. The other possibility is this term must be equal to 0. So I could write that as either t equals 0 or 15 minus 4.9 t is equal to 0. So t equals 0, that is already, I know what t is. For this scenario, I can plug that in a calculator, and when I do that, I get t is equal to 3.06. So this scenario implies t equals 3.06. So I have two possible solutions. Now we are going to take the two valid solutions from our math and connect them to the physics of what's going on in this problem. So for part A of this problem, we said here is my x-axis and here is my y-axis. We took a ball, we threw it, it went through the air and landed right there. So what did we really do when we plugged in numbers here? We were in a sense asking, at what time is the height of the ball equal to 0? And if I compare that question to the picture I drew here, I could see there are two moments when the height of the ball is equal to 0. When the ball lands and when the ball is initially thrown. So looking at these two results, I could associate t equals 0 corresponds to the moment the ball is thrown, and t equals 3.06 corresponds to the moment the ball lands. Both of these solutions are physically valid. They both correspond to a time when the height of the ball is equal to 0. Now, based on the context of what we're actually trying to do in this problem, we're interested in the time when the ball lands. So this is the number I'm going to go with. So at this point, I have enough information to go back and find the distance the ball travels. So the time the ball lands, we found, is 3.06. So now I am going to write x final is equal to x initial, v initial xt, 1/2 axt squared. And just like before, I have x final is equal to 0 plus 20, 3.06 plus 1/2, 0 for ax, 3.06 square. And I look at this right away. This term is just 0, so I don't need to worry about it. So I get x is equal to 20 times 3.06. X is equal to 61.2 meters away. So the distance traveled from the place we are when we throw it to where it lands is 61.2 meters from there to there. So I'd say 61.2. Now for part B of this problem, we are asked what is the ball's maximum height. So my definition of final and initial are prone to be redefined for a different part of a problem. So if I think about this problem, I want to know something about the ball when it reaches its maximum height. So I want to know something about the ball when it is right there. So what I'm going to do is I will now call this the final moment for part B of this problem. And I am going to look at what I wrote over here and ask, is there anything that is not correct here? So are there final values here that do not correspond to the final moment there? Well, clearly the height of the ball when it reaches its maximum height is going to be bigger than 0. So y final will be something bigger than 0. X final, it traveled 61.2 meters when it was here. It did not travel 61.2 meters when it was there, so I'll get rid of that. Vx, I say Vx here is 20. Is Vx still going to be 20? I'll address that shortly. Vy we didn't solve for, so I don't really need to do anything there yet. T final, well, if this is 3.06 seconds, this will be something less than 3.06 seconds. Gravity did not change. Gravity is assumed constant. Now, I could quickly say Vx is going to be 20 because if I just look right here, I get Vx equals V initial x plus AXT. But since AX is equal to 0, V initial is equal to V final, no matter what time I'm looking at for the horizontal component of velocity. So Vx initial is 20, Vx will always be 20. So I don't really need to change that at all. Ultimately, now in part B of this problem, what we're trying to find is what is this value of y final? What is this maximum height? So how could I think about that? Well, I look at the equations for y final and I could ask, well, this equation has a y final in it. That equation has a y final in it. So let's look at these two equations individually. Y final is equal to y initial plus v initial yt plus 1/2 ayt squared. I have Vy is equal to V initial y plus AYT. I have Vy squared equals V initial y squared plus 2AY y final minus y initial. What equation will help me find y final? So ultimately, the things I want are either y final is found here and y final is found here. So do I know y initial? Yes, I know v initial y. I do not know time. I know ay. I do not know time. Do I know vy final? I'll come back to that. Do I know v initial y? Yes, I do. I know ay. I do not know time. Do I know vy final? Again, I'll come back to that. I know that. I know that. And I know that. So either I need to know Vy final or I need to find time. And so, well, to find time, I need to know Vy final. So we'll just directly ask, what is Vy final? I'm going to draw this picture, but I'm going to zoom in on what we're looking at. So if I draw this picture, here is the arc, and here's the very top of the arc when the ball is in the air. So I zoomed in on the arc as the ball is flying through the air. And here is the top of the arc. The top of the arc is right there. Now, we could ask the question, we wanted to ask, what is the velocity of the ball right here? So what is Vy here? We know Vx is going to be 20. It is always going to be 20. But what is Vy? Well, let me draw the position of the ball at a few moments, like a few snapshots. So here is the ball, then it's here, then it's here, then it's here, then it's here, then it's there. Okay. From here to here, you kind of could see the ball move upward. Here to here, it moves up less. Here to here, it moves up less still. let's say the ball here is just before the top of the arc. Or the path that is traveling through the air would be a more proper thing to say. And right here is the moment just after the ball reaches its max height. Now, if we want, we could make have the ball be infinitesimally before the max height and infinitesimally after the max height. Did the ball move up or down when it went from here to here? Well, it doesn't really look like it. So one way you could think about it is if the ball doesn't move up or down, well, if it doesn't move up or down, then it has no vertical component of its velocity. The ball can be moving horizontally, but it doesn't need to be moving vertically. If it's not moving up, it won't have a positive velocity. If it's not moving down, it won't have a negative velocity, so it would have zero velocity in the y direction. The x direction still has that same 20 meters per second in the positive x direction, but the y component of the velocity is zero because it did not move up or down. There's another way we could think about this concept. So I could say when we are somewhere over here, there or wherever, all over here, the velocity of the ball is going to be greater than zero. The ball is moving upward when it is before it reaches its maximum height. All over here, the ball is moving downward. This is after the ball reaches its maximum height. So at every location on this side after you reach your maximum height, the velocity of the ball will be something negative. Now think about a number line. If you're on a number line, the velocity of the ball, the vertical velocity of the ball will be greater here than here because gravity is trying to pull you downward. So you're going to be moving upward at a greater rate compared to later on. Over here, you'll be moving down, but not too much. But gravity is going to work on you more, and when you get to here, you'll be moving down faster than you were up here because gravity had more opportunity to work on you to get you coming downward. If you think about a number line, you cannot go from positive numbers to negative numbers without passing through zero. And this maximum height of the ball, the vertical part of the velocity is zero. So I could say at max height, Vy is equal to zero. For the topic of projectile motion, which is I can also call for the topic of free fall, this is always going to be true. Now, I want to very explicitly say, so highlight it in your notebook, do whatever you need to do. At maximum height, the vertical part of the velocity is zero. That doesn't mean the total velocity is zero at the maximum height. At the maximum height right here, the vertical part of the velocity is zero, but the horizontal part of the velocity is going to be whatever it was initially. So it would be wrong to say at max height the velocity is zero. It is correct to say at max height the vertical part of the velocity is zero. The horizontal part of the velocity could still be whatever number it's going to be. There are two components to the velocity vector. So this is going to be a very useful piece of information for solving part B, finding the maximum height. If I look at these two equations, well, I don't know the time that the ball reaches the maximum height, but I do know the velocity in the vertical direction of the ball when it is at its maximum height. So I could say Vy squared when the ball reaches its maximum height. Here's initial, and here's final. For part B of this problem, we don't really care about this part anymore, equals v initial y squared plus 2ay y final minus y initial. So vy squared final is 0 is equal to, I'm just squaring it now, and again I'll solve the math in the next step. So 0 squared is equal to 15 squared plus 2, negative 9.8. Y final minus y initial. So at this point, I have numbers everywhere. I could just go ahead and solve. So I get 0 is equal to 225 minus 19.6y. And if I solve that through, I get y is equal to 11.48 meter. So for part B, the ball is 11.5 meters above ground level. In part C of this problem, we are asked to find the final velocity of the ball when the ball hits the ground. So in part A, we said the initial moment is the moment when the ball is thrown, and the final moment is when the ball lands. In part B of this problem, we said the initial moment is when the ball is thrown, but we said then the final moment will be defined as when the ball reaches its maximum height. Now that we want to know something about when the ball lands, we are going to assign again this moment to be the final moment for this problem. So we previously solved that the ball will land 61.2 meters away from where it's thrown. So I could set x final to be 61.2. When the ball lands, it is at ground level. So I could again set y final to be 0. And we are told that occurs at a time of 3.06 seconds after the ball is thrown. So I could write 3.06 seconds here. Now at this point, mathematically, finding Vy is going to be very easy. We need certain terms to find what Vy is, and we have every term we could possibly want except Vy. So this is just a straight up find an equation with Vy in it, plug the numbers in, and perform the calculation on a calculator. So I look at this, Vy is there and there. I'm going to go with this equation because it's shorter. So Vy I could write as v initial y plus ay times t. Vy is equal to, v initial y is 15 plus negative 9.8 times 3.06. And I hit enter on my calculator after plugging that in, and I find Vy is equal to negative 15. So V final y is negative 15. And at that point, I could say the final velocity is going to be Vx is equal to 20 meter per second, and Vy is equal to negative 15 meter per second. So at this point, I want to make a couple comments on things we've done. First of all, this negative sign is important. A positive y velocity implies you're moving upward, a negative y velocity implies you're moving downward. So if you were to say 15, that would imply you are saying the ball is moving upward when it lands. And that's not what happens when the ball lands on the ground. It's going to be moving somewhat downward. Number two, notice that these numbers are almost the same. The x number is the same, but the y component of the final velocity is just offset by a negative sign. And that's not a fluke of the numbers chosen for this problem. If you were to choose any problem at all, plug in any numbers for initial velocity, time spent in the air, angle, however you want to set up a problem. If I shoot an object in projectile motion up at some angle, it will have some initial velocity. Let's say this is an angle theta above the horizontal. The object will fly up, then it will be under the influence of gravity, hit the ground. When the object hits the ground, when it lands, this object will hit the ground at an angle, traveling at an angle of theta below the horizontal. The x component of the velocity, Vx or V initial x, will never change. So this V initial x, will be the same as V final x. And the y component of the velocity will be the same, except they'll be offset by a negative number. So the y component of the velocity, V initial y, over here. Here we're moving downward. This component of the final velocity will be negative Vy final will be equal to negative V initial y. Now, I am going to make a comment on this. Everything I said here is true provided that the ball is thrown and lands on level ground. If instead the ball were to be thrown but then land on the roof of a building, well, this is no longer going to be true. Vx will be the same because Vx is always constant, but Vy will not be the opposite of its initial value. Or if instead of landing on the roof of a building, the ball lands in a ditch, same deal. Another comment I want to make on this type of projectile motion. I notice people often want to say, well, the final velocity of the ball would be 0 because you throw a ball, it lands on the ground, and it comes to a stop. That is what happened. So the scenario you described is correct. That is what happens in the real world. When I throw something, it hits the ground and it eventually comes to a stop. But we are defining the final moment as the very instant the ball hits the ground. One way you could think about initial moment and final moment is don't think about the moment the ball is released or the moment the ball hits the ground. Think about the moment the ball hits the ground minus an infinitesimally short time before that. So instead of saying the ball hits the ground and when it hits the ground, ask what happens when the ball is barely above the ground. Because from the moment the ball is just one atom above the ground to the moment when the ball hits the ground, the velocity isn't really going to change. The position isn't really going to change. It changes by one atom, but that will just fall away in an approximation. So you could think of the final moment as the time the ball hits the ground minus an infinitesimally short time before that. And all the numbers you get for the final time will then be there. If you think about it, if the ball had a velocity of 0 when it hit the ground, if objects had a velocity of 0 when they hit the ground, it would not hurt if you fall off a really high thing. If you're standing on a chair and you fall off the chair, that hurts. The reason for that is you are moving when you hit the ground. Once the ground brings you to a stop, well, that's after the moment you first hit the ground. The final thing I'm going to say is let's take these numbers we calculated and let's look at the magnitude and angle of these vectors. So we said the initial velocity, I could write that as V initial had a magnitude of 25, an angle of 37, and then I could say, I'm just writing it bigger. Then I could say this V initial y is equal to 15. Here, V initial x is equal to 20. Let's do the same thing for the final velocity, see what we get. So here is the xy axes for the final velocity. It's going to be in the fourth quadrant. So I could draw the final velocity is going to be something like this. So here is my final velocity. And I'm asking what is the magnitude and what is the angle below the horizontal. So let's see, we know V final y is equal to negative 15. We know V final x is equal to 20. Let's find what this angle is, and let's find what the magnitude of that vector is. So, I am just going to draw this final velocity as a right triangle. I explicitly have a right triangle right here. So if I say this triangle has, this side has a side length of 20, this has a side length of 15, I'm going to assign the hypotenuse of this triangle the symbol lowercase v. When working with vectors, if you have a vector wearing a hat, that usually indicates the vector itself with the components specified or the magnitude and direction specified. If you have just the symbol without the hat, that very often implies the magnitude only. So the magnitude of this vector is going to be just v. So to find v, I could use the Pythagorean theorem. I could say side length of one leg squared plus side length of the other leg squared equals the length of the hypotenuse squared. So if I say 15 squared plus 20 squared equals v squared, I go through the math in this, I get v is equal to 25. So we get the same magnitude of the initial velocity as before. Now, if I want to know what angle this angle is going to be, I could just ask, what is this angle that I call theta? So to find theta, I could say, use any trig function you want, it doesn't matter. We already know this is 25. So I could say tangent of theta is equal to 15 over 20. That's opposite over adjacent. So I will take the tan inverse of both sides. Tan inverse of tan theta is equal to tan inverse of 15 over 20. Now, if I plug this in a calculator, on the right-hand side, I would get 37 degrees, and tan inverse cancels with tan, so I'm left with theta is equal to 37 degrees. Now, at this point, I inherently assumed the sides of all of this triangle I drew up here are all inherently positive, so I have to attach the number I found in my math to some physical reality. I know the ball is actually traveling downward, so this will be an angle 37 degrees below the horizontal. So this is an angle 37 below the horizontal, or I could write it as negative 37 degrees if I want. Think about when we talked about counterclockwise rotation versus clockwise rotation, and I could say this vector has a magnitude of 25 meters per second. So again, this result I have of the final speed of the ball, which is the same as saying the final magnitude, the magnitude of the final velocity, the angle at which the ball is moving when it hits the ground, only applies when the ball is landing on level ground. The ball is thrown from a certain height, it lands at that same height, which in this case was a height of 0.